colleagues, I welcome all of you at the second session of this very beautiful meeting. Our first speaker will be Ferenc Iglói from the same institute as I am. So he shared his screen. You probably already see the logo of the Wigner Research Centre for Physics. He will talk about Reentrant, random quantum Ising antiferromagnet. So please explain us the secrets.
Okay, thank you very much. I am very happy to speak in this occasion, and I first would like to thank the organizers, mainly to Zoltán, to be able to put up this beautiful meeting, which was actually the first in the history of MECO to be online. And as we see, it seems to be really a success. Okay, let's go to the subject. So it is about perhaps the simplest quantum system, the quantum Ising chain, which is somehow made random, and we use antiferromagnetic interaction here. Okay, this is made, this research in collaboration with Jean-Christian Angles-Doriac from Grenoble, Peter Rajko, he is in Kuwait now, he is otherwise Hungarian, and Heiko Rieger is in Saarbrücken. Okay, and let's see our model. So this is a Ising chain. The variables are Pauli matrices at site I. It has a length of L. And the first term is the classical antiferromagnetic interaction between nearest neighbors. The quantum effect is made by the transverse field, which is this term here. Since at the same position, the Pauli matrices, we all know, do not commute. And finally, in the antiferromagnetic model, we can introduce also a longitudinal field. And even in the presence of a longitudinal field, we have interesting physics here. What we make here random, this is the interaction and the transverse field. But at the same time, we keep this longitudinal field positive and non-random. So in this way, we wanted to get rid of random field effects. Okay, now let's start with the clean system. In this case, both the couplings and the transverse field are constant. The antiferromagnetic interaction is taken to be unity, and we denote by gamma this transverse field. And this is the phase diagram, which consists in the plane of the gamma H phase diagram with J equal 1. There is an antiferromagnetically ordered phase. If the gamma the transverse field is not too strong, and also this longitudinal field is not too strong, this is antiferromagnetic. And here the ground state is in an up-down, up-down, up-down order, can be seen schematically. If we leave this phase, then due to strong longitudinal field, all the spins will point in direction of this field, and there is a phase transition in between. And actually, there are two fixed points of this phase boundary. One which at h equals 0, and the second is blue one, which is without quantum fluctuation at gamma equals 0. And these points, we know the clean critical behavior exactly. So in that very point here, this is the transverse Ising model. This is in the universality class, the transition in the universality class of the classical two-dimensional Ising model. So this is a well-known point. Here down, here we are without quantum fluctuation. Here we have a classical multi-critical point. Actually, the antiferromagnetic and the ferromagnetic phases change at the first order transition point. There is a sharp changes here. And in between, there is a critical line, which is expected that the transverse Ising model is attractive. So all of this line, we have the transverse Ising model universality. And which is interesting that this model has been experimentally realized in ultra-cold atomic gases not long ago. And it is very probably the most accurate demonstration of a Ising or a quantum Ising transition. So this is, I forgot to say, everything is in zero temperature actually. So this experiment is also made at ultra cold, so very low temperature case. Okay, now let's go to our problem, which is the disordered model. Both the couplings and the transverse field are random, and the distribution are taken in a box-like form, which is parameterized by one parameter. Here, this J0 is taken to 1. So this is between 1 and 2, having a value everywhere is 1 of this distribution. The other has a parameter gamma 0. If gamma is smaller than 1, this whole is shifted to the left and has a bit higher value in order to be normalized also. Okay, and we have, as I said, the homogeneous longitudinal field. And let's see what is going to happen with this clean system that we studied before. And let's see the situation, what is happening with the fixed points, what I described before. Okay, so for the transverse Ising model, the transition will be the random transverse Ising model, which is practically exactly known the behavior. It has an infinite disorder scaling behavior at the critical point, which is here just gamma 0 equal to 1. Strong disorder renormalization group calculation by Danny Fisher showed that there is very strange scaling behavior between the energy scale, the log energy related to a power of the size of the length of the system with an exponent of 1/2. And the average correlation function defined between two spins as a distance of r, where this bracket shows the average over the ground state configuration. It's a quantum average, as this over bar shows the disorder average. We have actually a power law decay with an exponent which is related to the golden mean ratio. This is also an exact result. Okay, the next point, what is going on to happen in this classical limit when gamma goes to 0? When we go in this limit, one can make a simple consideration. If this longitudinal field is small enough, actually smaller than the sum of the two smallest couplings, one in the odd position, one in the even position, then the ground state is still antiferromagnetic. If, however, this is not the case, it is stronger, then this block will be flipped as it's shown here, since it is energetically favorable to have one more site, one more spin pointing in the direction of the external longitudinal field in the cost of the two couplings, which are now not favorable. Okay, if we then make disorder average calculation of this correlation function that I shown before, where for a finite system, we took the distance between the largest one, between the first and the L+1 - 1 position. Then these are the average correlation function. For smaller values, for 32, it is going like this. Increasing the size, it is going more and more sharp. This is for 2 to the power of 17. This can be also made by a spatial form of this minimization, numerical minimization calculation. So it is evident to see that here we have a jump. However, the length scale at the same time is shrinking towards 0. So the width of the transition shrinks as 1/L, but at the same time there is a jump. So this is a random first order transition, which in this sense it is a mixed order transition with a jump having also a diverging length scale. Multiplying this difference with L, we get a scaling combination, which is given here. And in terms of the scaling combination, we can put together the different curves which were shown before, which are very well on the same curve here. And actually one can make an analytical calculation with using extreme value statistics if we just one, or if we consider without domains or with just with the 2 domains in the system. And this is actually the analytical result given by this form, which is very well in the form of the numerical calculation. Okay, so we are now at this situation that here we have a infinite disorder fixed point. Here we have a random first order transition. And now we are in the most interesting case, what is going to happen in between. So we are now in this region and we do the following. We fix the value of gamma, let's say for this value of 0.2 here. And for different values of the age, we calculate this average correlation function that I shown before. So this average correlation function, fixing this value of 0.2 and taking this calculation for different values of L by increasing values. This is for 8, 16, 32, 16. So for different values of age, we see actually that there is a difference between the different phases what this DMLG density matrix normalization group calculation shows. Here this correlation function is positive. This is the paramagnetic phase. Here below, this is the antiferromagnetic phase, and in between these points which are just separating, and here this value is 0. These are the finite size transition points. So having this finite size transition point, one can make an extrapolation for different sizes. So actually here I show this extrapolation from 8 to 16, and here this curve is more or less an illustration what we expect as a phase boundary which separates the antiferromagnetic order phase, the paramagnetic phase, and which is interesting that here before there was no reentrance, it was started already going to the left, this boundary. Here we have a reentrant phase transition. So here, seeing that here, this is infinite disorder scaling, below random first order. And in between, I blow up this part, this here. It is seen that there is a reentrant phase starting from small gamma, we are in the paramagnetic phase. Then by increasing gamma, we enter to the antiferromagnetic phase. So this is a typical example of order through disorder. So through quantum fluctuations, we can gain actually antiferromagnetic order in this case. And then increasing further on, we leave the antiferromagnetic phase and we enter to the paramagnetic phase. The phase transition upwards is expected. It is not sure, but continuing the previous fixed point, it could be infinite disorder type, and below it is random first order. Okay, so this is the phase diagram. And actually one might ask the question, what is about the phase transition behavior in between? So here in this regime, actually we try to make a strong disorder renormalization calculation in the case when this H is small. So we are very close of this fixed point, and we are interested what is going on here. So in this strong disorder renormalization group, which was already used by Danny Fisher for the for the model without transverse field, without longitudinal field, the following should be made. Actually, one looks for the gaps in the different position. For couplings, it is just the value of the coupling. For sides, it is a combination of the two fields in this way. And actually, one sort these gaps in descending order. The largest is omega. This side is eliminated. This side is eliminated, and new terms are generated between the remaining sides. And this procedure is iterated further on. So here just a short explanation. If we have a strong, very strong coupling, then these two spins move always coherently. So we can actually define a spin cluster in the term of an effective transverse field, which can be calculated in a second order perturbation calculation, and getting this result which is written here. And we will have the sum of the two longitudinal fields in here. For a strong transverse field, in that case, if there is a strong transverse field, then this is eliminated since it has no contribution to the susceptibility. And actually a new coupling is generated between the two remaining sides. Its value is calculated perturbatively. And we also have a rule how to put this two fields which were originally here. The longitudinal field is added here and here half in order to get rid of any problem, any effect.
Ferenc, the 15 minutes are over, so please come towards a conclusion.
Okay, I am going to the conclusion. So if we make a numerical iteration, then we see this one for the H equals 0 when we know that it is a infinite randomness fixed point, and we see very much similar if we let this point a bit further. So actually, we get the conclusion that this is actually numerically also in the infinite disorder scaling. We see a similar conclusion from the DMRG study. And here are the conclusions. Here's the phase diagram. So actually having a random transverse Ising model, infinite disorder scaling, very probably all of this part. We have random first order transition close to small gamma. And here there is a Reentrant antiferromagnetic phase. Okay, so we can ask several open problems. I am not going here to the details, but thank for your attention. Thank you very much.
Thank you very much. Now it is open for a few questions. Can you go back to this last slide with your picture on that? 2 slides back.
This one?
is it correct that there is a kink in your phase transition line, or it is just numerical here up?
No, here up. No, it is, how to say, it is not a real kink. Yes, it is just how to say, a numerical.
Okay, that was the technical question.
Oh, no. Actually, it should be continuous.
Smooth.
Without kink. Yes.
So, does anyone has no special questions to Ferenc?
Yes, I do. May I, Yuri Holovac?
Sure.
Thank you for this very nice presentation. The question is the following. The larger, it concerns also this picture. The larger the age, the smaller the difference between gamma values when we enter and when we leave. Yeah? What happens when this difference approaches zero? What happens in this?
Here in the, you ask in this region.
I ask, you have reentrant transition, and then the difference between the two values of gamma decreases with age. What happens when this difference approaches zero?
Actually, in this region you can make a perturbation calculation, a second order perturbation calculation very close to this point. And actually, you can see that if you make this perturbation calculation, the antiferromagnetic states somehow have a higher weight as you increase gamma. So the correction which is coming from due to this transverse field is becoming stronger here than here. So here you have already a gap, and this gap is going to vanish if the gamma reaches actually a given value. I don't know, this was precisely what you asked, or?
Almost, yeah, thank you.
Okay, thank you.
Thank you. Is there a last short question with short answer from somebody? If it's not the case, we thanks Ferenc again.
Thank you.
And then I call our next speaker, Dr. Schreiber, Nir Schreiber for Bar-Ilan University. So please share the new screen. Yes, we have it.
So thank you very much. I am Nir Schreiber. Thank you for the introduction. And I would like to thank for the organizer for inviting me to speak today about unusual changeover, the transition nature of local interaction POTS models. And this is a joint work with my my PhD supervisor, Uven Cohen, and Simi Haber, and Gidi Amir, and Baruch Barzel, all from Math Department in the Bar-Ilan University. So, so we're talking about an unusual phenomenon. So first we have to say a few words about the convention. So the general convention that is a spin system which has the same dimensionality and described maybe by Hamiltonians that preserve the same symmetries belong to the same universality class. So usually when we think about universality, we think about the behavior of the physical observables, right? The divergence of the specific heat or magnetic susceptibility near the critical point. And we claim that all the systems which have a local interaction model, regardless to the general to the interaction content, so they have the same critical exponents. But one might extend the notion of universality beyond the behavior of the physical observables near criticality. So, for instance, Baxter in the early 70s considered the POTS model, the pairwise standard interaction, nearest neighbor interaction POTS model. And he calculated the latent heat, and for more than 4 states, the latent heat was finite, and it has vanished for Q equals 4. So based on that, Baxter has conjectured that if the number of states is no larger than 4, then the transition was second order. If it's more than 4, then transition was first order. And in a few, in 2 remarkable and very mathematical and technical detailed papers. Dominique Coppa and co-authors have rigorously proved this conjecture. Now, if we talk about a universal phenomena in some sense, so this can be manifested, for instance, in this work of Ninhus from late 70s, when based on renormalization group considerations, they have showed that, in fact, the result of Baxter is lattice independent and probably interaction content independent, provided that this is very much important, provided that the interaction is local. Because there are other works like this work from 2007 that show that if you consider non-local interaction, finite but long range, then already if you look at three-pot states, then you wind up with the discontinuous transition. But what I would like to try to convince you today is that even if you consider a local interaction model, then the notion of universality is still controversial. In fact, some say that it may not exist. So there is another model, for instance, the model studied by Tamua et al. From 1808, I believe, from 2008, that they have considered the standard model, but they did not keep the number of pot states fixed. They let it vary. So in opposed to that, and they showed that if the number of states is large enough, then you will have a first order transition at any Q. So what they have considered is Q states, the usual Q states that control the energy, and another R state that control the entropy. And if R is large enough, then no matter what Q is, you will wind up with the first order transition. But it is a kind of unnatural model in the sense that the number of states is exceed beyond the usual number of states which controls the energy. And what we suggest is a more maybe natural model that preserves a number of states. And it can be described by this Hamiltonian. So this is a phase interaction model, and this O delta function notation means that if you consider spins residing on the vertices of the elementary lattice cell, that locally, if all the spins have the same pot state, then the energy is lower, then it is left unchanged otherwise. So if one wants to evaluate the partition function, one essentially can map the problem into a problem of graph counting. So here, for instance, in this illustration, you can see a spin configuration realized by a graph. So you have here 4 clusters in this graph, and the 3 different colors denote the fact that this graph denotes a model with at least 3 states. Now, since we are interested in the behavior near criticality, so we can, and since of course the problem of graph counting is very hard, we can approximate the problem into a problem of a single graph, a single large component, typically scales as the volume, and evaluate this expression. So we wish to evaluate the number of such big clusters with K faces and M sites. And basically, this turns into a problem of evaluating what we term lattice beasts. So this is a typical lattice beast, a triangular lattice beast. So this beast is composed from 1, 2, 3, 4, 5, 6 lattice animals. And each animal, so a lattice animal is a collection of faces interacting sidewise. And since it is known that the number of animals is exponential, then it is plausibly to assume that, well, you have maybe a larger set, so this is also exponential, probably with a larger exponent. Now we distinguish between what we call simple BIST, which characterizes first order transition. So in first order transition, in criticality, you have a large rectangular, say, component, or a cluster with a boundary which scales slower than the volume. And if R is the minimal asymptotic sites per phase, then of course a BIST has a minimal number of sites per phase, and vice versa. It can be easily shown that a simple BIST has at most R sites per phase, and also that the number of such BIST is sub-exponential. So this means that if you go beyond the simple BIST, then you wind up with exponentially family of quasi-fractals or fractals, which goes at rate mu, and mu essentially depend on some positive parameter delta, which control the deviation from the simple BISTs. Now imagine you construct a large cluster made of these quasi-fractals. So if you have m sides, then you decrease the entropy in this amount, and because these guys grow exponentially, you gain the entropy proportional to this term. And of course, you have a constrained perimeter, you have a negative perimeter term, which is not important. And of course, higher order terms that you can ignore. Now, if you look at the change in the free energy, when you construct such a large cluster, then if K is the energy, right? The energy is proportional to the number of phases. Then if you look at the temperature T star, so T star is a temperature which eliminates this term, namely it balances the entropy loss versus the energy gain when you construct the simple cluster. Then you have that at T star, the change in the free energy is non-negative, provided this term in the brackets is no smaller than 1. And by this, you get some kind of measure, this QS, so QS is not necessarily integer. So you get a measure beyond which, if you go beyond, for Q beyond this QS, larger than QS, you have that this term is non-negative, meaning that it is entropically disadvantageous for the system to create these quasi-fractals, and instead, to minimize the entropy loss, the system creates a large simple component. In other words, it undergoes a first order transition. So it can be shown that T star is a lower bound of the critical point, and you have a first order transition for Q larger than QS. And of course, conversely, if you have a second order transition, then you have some exponential family mu with the parameter lambda, and this inequality holds in the other direction. So now our mission is to evaluate QS. So for that purpose, we consider pure animals. So by pure, I mean animals which, or beasts which do not interact sidewise, right? Because if you look at the hexagonal lattice, you cannot tile the plane with two adjacent hexagons which has mutual vertices only via mutual edges. So denote the number of sites belong to 1, 2, and 3 faces by N1, N2, and N3. And then you wind up with this system of linear equations. So this is the total number of faces and total number of sites. And the total number of boundary sites is B. And of course, it is composed by N1 and N2 type sites. And the last equations follows from the fact that if you travel along the perimeter, then each time you cross a one type site, you gain a curvature of pi/3. And each time you cross a N2 type site, you lose a curvature of pi/3. And of course, the total curvature is 2 pi. And then you have that N1 minus N2 is equal to 6. Sorry, and so this equation is this measures the deviation from simplicity, say, in the hexagonal lattice, and this is the asymptotic number of sites per phase the minimal asymptotic number of side spaces in the hexagonal lattice. And if you plug this, you solve this equation for B over K, you wind up with this, this relation. So the reason that we focus on the hexagonal lattice is that we wish to evaluate the number of lattice anomers with size K, with K faces. And the way we want to do it is to bound it by the number of self-avoiding walks on the hexagonal lattice. And since we do not allow for beasts that interact via mutual vertices, then this is exactly the case. As I said before, on the hexagonal lattice, right? You are not allowed to have local loops, right? So indeed, you can say something about, you can evaluate the number of animals by bounding them by the number of self-avoiding walks. So this is captured by this relation. You take the supremum to get the maximal boundary. And then if you plug this to this equation, you wind up with this estimate on the growth constant of these creatures. Finally, you have to take the supremum, and then you have that this QS is approximately 3.4, and what is important that it is smaller than 4. So indeed, if Q larger than 3, you have a first order transition. And in this sense, this notion of universality that would have been expected is in some sense violated. And of course, you have that the second order transition occurs when QC, and QC is the maximal integer for which a transition is continuous, and QC is no larger than 3. And okay, so I don't have much time left, so I go briefly into some nice simulation results.
We used 15 minutes, so please work towards conclusion.
Yes, okay. So let me just say, do I have another 1 minute to discuss simulations or to skip it?
Talk, and then stop.
Okay. So here you can see the variation of the specific heat at the internal energy with temperature. And you can see that for the 3 and 4 state model, you have, as opposed to the 2-state model, you have narrower and larger peak. And here you can also see signs for the occurrence of latent heat for the 3 and 4 models versus a smooth and slow variation in the 2-state model. And finally, if you look at the probability density function, the energy probability density function, you can see a typical first order 2-peak scenario versus a single peak scenario for the 2-state model. And here you can see the variation of the scaling of specific heat with linear size, lattice linear size. You can see typical volume scaling versus a logarithmic divergence, as you can see in the Ising model. Okay, I will skip this chart and drop to conclusions. So I hope I convinced you that lattice-based is govern the Q-dependent transition order, and the notion of universality is violated in the sense that even though the interaction is local, it does not mimic the behavior of the standard model, and that the theory is well substantiated by Monte Carlo simulations. And thank you very much for your attention.
Thank you very much. Are there questions? Maybe I may start with my own naive question first. How do you decide which kind of lattice you use? Triangular, honeycomb, quadratic? What is here the...
So, yes, so, okay, so we have chosen the honeycomb because it was crucial to since we do not know much about much about the growth rate of those quasi-fractals which control the transition. We have to evaluate them in some sense, and for this purpose, it was convenient to use the honeycomb lattice, because in the honeycomb lattice we could have bound them. This is the reason we have used the honeycomb lattice. This is impossible to do on other lattices. Because on other lattices, because the interaction allows for objects, what we call beasts, that may grow larger than the animals, we cannot say much.
No restriction, I see. Any other questions to this talk, please? Since it does not seem to be the case, we thank the speaker again and move on to the next one. So maybe I just announced that the next keynote talk is going to be given by Hiroshi Kori from University of Tokyo. And it is about tackling complex dynamics in biology and chemistry with phase oscillator models. So we are looking forward to your explanation how to make biology and chemistry as simple as physics.
Can I already start?
Please, you can start. Yes.
Yeah, okay. Okay, thank you. Thank you very much for the introduction. And I'm thankful to the organizers for making this conference under this extremely hard situation. And I'm also thankful to the audience for joining my online talk today. I really wish everybody's safety and happiness. I'm Hiroshi Kori from Tokyo University, the University of Tokyo. Okay, so I'm a theoretical physicist working on synchronization. And let me start with some movies, interesting movies. The first movie is a kind of accident happening in 2000 in London.
Something unexpected happened. People changed the way they walked in reaction to the movement of the bridge. To balance themselves, pedestrians spread their feet apart, creating a significant lateral, not vertical force. More importantly, the people's reaction was almost identical. Everyone stepped the same way at the same time, creating a synchronized rather than random force. The frequency of this force matched the natural frequency of the bridge.
Okay, so as you can see, the pedestrians interact by a movement, lateral movement of suspension bridge and synchronize. And this caused a dangerous situation in this case. And a similar phenomenon can be easily reproduced by putting metronomes on the suspension bridge. And you can see the communication between 4 metronomes. Let us see it. So 4 metronomes, and starting from kind of random initial conditions. And you can see the communications via vibration of this bridge. And you can see now we have 2 clusters, one with small amplitude, the other with large amplitude. But this state is unstable. And they try to find another state, and they finally find a stable state that is synchrony. Now the amplitude and phases are almost the same. Okay, and also cats synchronize, but this is, you should not take this seriously, okay? Anyway, so there are many questions, so many questions in synchronization. And here I list up some of general questions. And one is how to model and under what condition do oscillators synchronize? And there are many complex phenomena in coupled oscillator systems and many types of spatial patterns, temporal patterns, or spatial temporal turbulences, and so on. and also noise effect on synchronization, and also coupling network effect on synchronization, and also what is the function of synchronization, such as you can think of some biological or energetic aspects, and also how to control synchronization, how to control the synchronization dynamics. And also there are many applications in biology, in medicine, in engineering. And these blue lines shows basically the content of this talk. And first I will briefly talk about parameter theory and using the method of phase oscillator models. I will tackle these kind of problems, and one is noise effect, the other is the control, and the final one is application in biology. And this is actually about jet lag. And I will show you some very, very new human data as well. Okay, so at first, introduction of phase oscillator models. And phase oscillator model is a very simple mathematical tool that shows rich dynamics and also have broad applicability. In dissipative systems, a rhythmic unit is usually described as a limit cycle, and a metronome provides a wonderful example. Here, I start this metronome from a low amplitude, and it eventually arrived at a certain periodic state. Okay, and in this case, I started from a large amplitude, but it eventually arrives at the same periodic state. Okay. Sorry. Okay. So this means that in state space, there is an isolated and asymptotically stable cycle exists. And this red curve is so-called limit cycle. And this does not exist in Hamiltonian systems, but quite common in dissipative systems. And a single oscillator, for example, metronomes or genetic oscillators in biological organisms, it's already quite complicated. But if it is perturbed only weakly, we can describe it by a single variable model, so-called phase oscillator model. So this is a limit cycle oscillator, and suppose that perturbation is given as a time varying function, the PT, and the phase oscillator model read this equation. The velocity of phase has some natural frequency omega plus the coupling strength, copper, and PT is a signal perturbation. And here, very important function Z comes. And Z is called phase sensitivity function. And this is a 2-pi periodic function describing at which phase the phase increases or decreases with, for example, positive signal. So the response is phase dependent in general, and this is coded in this function Z, phase response curve, or phase sensitivity function. And the derivation is as follows. And actually, this is the kind of detail and not that complicated, but I skip this slide. And with the phase model, we can model, for example, flashing fireflies. Suppose that we have two flashing fireflies, and they are interacting using light. They are flashing. And now we model in this way. So this phi I determines the timing of flash of firefly I. And omega 1 and omega 2 are natural frequencies. And P of phi is a light emission. So at certain phase, this firefly flash. And the interaction is described in this way. So it has the phase response curve of Phi1, the Firefly 1, and also the flash from the Firefly 2, and the similar equation also for phase 2. And an important thing is, in this kind of modeling, the natural frequency omega and phase response curve Z and also signal P are quite often experimentally measurable. And for example, the Z of real fireflies is measured in this paper. Okay, so in a phase oscillator model is also good for describing the real world systems. And the phase oscillator models can be further simplified using the method of averaging. Suppose that we have this model and assume weak coupling. Weak mean, by weak, I mean this coupler is small compared to these natural frequencies, omega. Then the phase difference between two oscillators does not significantly change within one cycle. Therefore, in a good approximation, we can average the equation over one cycle for fixed phase differences. And this results in this kind of simplified equations. And here, f function, now the interaction is given as a function of phase differences, is a kind of convolution between the phase response curve and signal function P, ZP. Okay, and this phase equation is actually much more tractable, much more easy to tract the deal with than this previous phase model, because this has higher symmetry. Actually, now, because the coupling is a function of phase differences, now this is originally two-dimensional system, but this is essentially now one-dimensional system. The essential variable is only the phase difference in these equations. Okay, and as many of you may know, the Kuramoto model looks like this one. So by assuming simple coupling function, this sine function here, and simple network, in this case, the global coupling, or you can also say a mean field coupling, we have so-called the Kuramoto model. And here, omega I is natural frequency, and this is usually taken from a distribution, probability distribution, such as Gaussian or Lorentzian, so random numbers here. And the Kuramoto model usually refers to the model with infinite N, but let us first consider its finite version. For example, in this simulation, N equals 20. And here I plot the omega I tilde as a function of coupling strength K. And omega I tilde is the actual frequency defined as the long time frequency of each phase, okay? And at K equals 0, the oscillators are totally independent. So these values show the natural frequencies of individual oscillators. And as coupling becomes larger and larger, you can see some kind of synchronization. The actual frequency make a cluster becomes identical. And around here, all of the oscillators has only one actual frequency. So all of them are frequency synchronized. So this kind of dynamical behavior occurs in this model. And you can also see the output of oscillator assembly. In this case, the number of oscillators are 20. And let us see this mean signal. And this is in the absence of coupling. They're independent, but because of some kind of fluctuations, we have somehow large amplitude oscillations as well. And K equals 0.3, we basically have the same situation as in the absence of the coupling. But around from k equal 0.6 or 0.8, you can see clear large oscillations. Actually, the system begins to synchronize significantly around here. We can look at this transition by observing the order parameter. In the study of synchronization, we usually use this complex order parameter R and also so-called Kuramoto order parameter, this capital R. So R is a kind of the center of mass in the phase plane, the complex plane. So on the unit circle on the complex plane, you place the the oscillators on the complex the unit circle, and and this red line is from the origin to the center of mass, and the length of this vector is Kuramoto order parameter. This is the same as the magnetization in XY model. And here is a plot of R as a function of coupling strength K. And you can see the gradual increase. There could be the transitions around here, but not clear in this simulation. But if we use a larger oscillator assembly, we can see clear transitions here. And Kuramoto shows that at n goes to infinity, we have R equals 0 for kappa smaller than the critical coupling strength. And for R larger than the critical coupling strength, we have this type of non-zero value. And this transition is, some people call it Kuramoto transition. And in this simulation, we have Kc equal about 0.8 in the limit of n infinity. And you can see roughly agrees with these numerical simulations, okay? Okay, so now let us move on to my contributions on synchronization study. So first issue is a noise effect on synchronization, published some time ago in this paper, the 2010. So this is noise-induced synchronization in the large population of coupled oscillators. So this is a kind of very, very brief overview of noise effect on synchronization. So if you have identical oscillators, so the omega is all the same, and infinite number of oscillators, plus coupling, global coupling, sorry, the sigma is missing here. This is the global coupling, and also plus independent additive noise. And here noise is Gaussian white noise. And this system is synchronized if the coupling is larger than the noise strength. So this is already shown by Kuramoto in 1984. In another case, we have independent oscillators plus so-called common noise. Common noise is kind of important in real systems because this describes kind of environmental fluctuations such as the room temperatures in the experimental room. And the effect of common noise on oscillators is also interesting. And in this modeling, we usually consider the phase response curve as well. And here PT is a common noise. This is white Gaussian noise. In this case, this is a work by Terama and Tanaka in 2004. And they show that this system shows synchronization only when the oscillators are all identical. Okay, so how about coupled non-identical oscillators plus common noise? Does the common noise promote or inhibit synchronization? So this is a question which we had. And this is the model which we considered. So we considered Kuramoto model plus common noise. So So suppose that we have Kuramoto model here. Sorry, again, the sigma is missing here. Plus additive, no, the multiplicative noise. So the white Gaussian noise times the phase response curve here. And if we take continuous limit, we arrive at this kind of equation. And here F is a phase distribution of oscillator having natural frequency omega. F is a function of omega and phase and time, okay? And R is a complex order parameter given by this equation. So this one is the same as the previous one, but this is a continuum limit version. And so how to analyze this equation? So we have a powerful tool, so-called Otto-Antonsen theory, proposed in 2008. So this theory argues that there is a low-dimensional attracting manifold in the system, in the Kuramoto model and its variant, including this class. And the probability distribution on this manifold is given by this one. A certain functional form can be assumed. And now, by considering the Lorentzian distributions for natural frequencies, we obtain this very simple equation. Now the system is reduced to the two-dimensional systems. This is so-called Stewart-Landau oscillator plus some noise effect here. Okay, so now R is complex, so this is basically a two-dimensional system. And by putting R in this way, and here A is a kind of our order parameter, we can derive Fokker-Planck equation for the distribution of A that is described by Q of A. And that is as follows. This doesn't look so complicated and easy to actually analyze. And the stationary distribution of this Fokker-Planck equation and its maximum, A max, are found as in this way. Okay, so here, if we take this A max as an order parameter of this dynamical systems, then we can say that the synchrony does not occur if K plus D is smaller than 2, and synchronization occurs for otherwise. Okay, and the important point is transition point decreases by the strength with the increasing noise strength D, as you can see. So K plus D is now important parameter. And this is a comparison of analytical and numerical results. And okay, so let me first explain this slide, this figure. So this is the order parameter A max, the maximum of the A, and this is the coupling function K. And in the absence of noise, I set the width of the frequency distribution such that the critical coupling strength becomes 2, so that the phase transition occurs at 2. And actually this A corresponds to the square root of Kuramoto order parameter. So that's the reason why we have the not square root line, but the straight line here. Okay, now if we are below the critical coupling strength, say, for example, 1.99, this shows a snapshot of the phase distribution of the system. And these black points shows the phase distribution in the case of no noise, in the absence of noise. Because this is below the critical coupling strength, we have flat distribution, so no synchrony occurs. But if we add noise, now the noise strength is 0.02, we have unimodal distribution in the phase. So we have synchrony now. And with these kind of numerical simulations, we confirmed our theory works well. And for example, if the noise strength is 0.02, this order parameter increases in this way. So the phase transition point changes from 2 to 1.98, and even stronger noise, we have earlier synchronization point here. Okay, so we now find that common noise promotes the synchronization. Okay, so it seems that we can play and have good understanding of synchronization with phase oscillator models. But I ask myself actually, are they really useful or not? So with phase oscillator models, can we quantitatively predict and control the collective dynamics of real world oscillators? So this was the question which I had. And with this motivation, I began to work with a Hungarian chemist, István Kis, and set this problem. So suppose that we have a population of oscillators interacting or independent. Anyway, so we have a population of oscillators. And suppose that we have a target collective behavior, for example, synchrony or desynchrony or clustering. And we try to steer the system into the target behavior which we set using delayed global feedback by observing the oscillator state and transform via some kind of equations and give a feedback signal to the entire population as a delayed global feedback. And we ask ourselves whether we can steer the system into our target behavior. And for example, you can think of this system. So suppose we have pedestrians on the London Millennium Bridge, and we can observe the pedestrians walking, and maybe we can give a feedback via strong noisy sounds and try to desynchronize the system. Okay, so, and this is our proposed methodology. So actually, before that, I explained the usual way to study the synchronization, which I already explained. So there is an experimental system, and we can build up the detailed model and analyze and arrive at phenomena. This is one possible way. Or one can derive the phase oscillator models from experiments directly or detailed model. And from the phase oscillator models, one can further simplify using averaging from type phase oscillator model and arrive at phenomena. That is a possible way. And so this is our proposed method. We go this way reversely. So the crucial assumption is that we know the phase response curve Z and output function X of an isolated oscillator are known, and how to steer the system into the desired state. So the first, we find a coupling function F in the phase model, realizing the target behavior. And now here you may consult the literature, what kind of coupling function F result in what kind of phenomena. For example, synchrony, desynchrony, or clustering. Now, then construct global feedback function P with the form, with this form. And here, X is a signal from individual oscillators, and Y is the average over the population. And here, the parameters are the strength of feedback C1, C2, and so on, and also delays tau1, tau2, and so on. We can construct this P function such that the convolution between Z and P result in the desired function F. Okay. And by implementing this feedback P in the experimental system, we should steer the experimental system into a desired phenomena. And this is experimental verification done in University of Virginia. We used the coupled electrochemical oscillators plus feedback given by the potential given to the potential applied potential V in this way. And here X is calculated from the current from individual oscillators. And this is the result. So at first we consider 64 independent oscillators. This is the experimental result. And before we set that feedback signal, we have desynchronized state. And now if we switch on the feedback, we have synchrony or 2 clusters or 3 clusters, 4 clusters, which we desired. Okay, so we succeeded to make this cluster state. Also, desynchronization is possible. So in experimental system, by adding this global coupling, the resistance here, making a global coupling between oscillators, and with that feedback, electrodes synchronize. And we can make the signal using our theory and feedback signal. If we apply that feedback signal to the system, we succeeded to desynchronize the system. And if we switch off the signal, the system backs to the synchrony. Okay, so in this work, we could predict what kind of signal can steer the system into a desired system quantitatively. So phase models work for the quantitative control of a chemical system. Now I got confidence and I decided to tackle biological problems. Okay, so this is issue 3 about the mechanism of jet lag and a method to circumvent it. So this is in collaboration with a biologist in Kyoto University, Dr. Yamaguchi and Dr. Okamura, and these are published from these 2 papers already. Okay, so let me first explain what is our biological clock. So our circadian clock is about 24 hours clock in our body. Our circadian clock is orchestrated by SGN. SGN is a small tissue in the brain, so-called the suprachiasmatic nucleus. And this tissue consists of thousands of neurons, and each neuron is a genetic oscillator with a period of about 24 hours. So we have actually a large population of oscillators in our brain, and this oscillator have 24 hours rhythm. And this tissue is known to control the clocks, biological clock in the entire body. If you lose this tissue, you will lose this circadian rhythm. For example, sleep-awake rhythm or some kind of temperature rhythm as well, body temperature rhythm. And also here, I show a movie. So this movie shows each neuron's genetic activity. And here, each neuron's genetic activity is visualized using bioluminescence. And you can see clear synchrony across the tissue. And this synchronization occurs, you can see the period is about 24 hours, and you can see nice synchronized oscillations for long, at least in this experiment, 4 days and 4 days. And also, you can also see a kind of large phase distribution in this synchronized state. You can see the earlier phases and the delayed phases. So this is actually important property. I will come to this point later. Okay, so as you know, when we experience a long distance trip across several time zones, we have jet lag symptom, which I missed in this conference, unfortunately, anyway. And here, this is an experiment using mice. And here, this mimics the situation of jet lag. Here I show the activity rhythms under light, dark cycle of a mouse in a cage. And this is days, and this is 24 hours. And each lines correspond to each day, 1 day. Okay, and this white region corresponds to the light phase, and this dark region corresponds to the dark phase. In the cage, light is on in this light phase and off in this dark phase. And blackbirds shows the frequency of movement of this mouse. And because this guy is nocturnal, he is active during the night phase. And at this day, this LD cycle, light, dark cycle, is phase advanced by 8 hours, and which correspond to the eastbound trip. For example, from Japan to Los Angeles, or maybe from mid-US to East Europe. Okay, and you can see the activity onset, try to adjust to the new schedule, but it takes really long time. And this is what actually we quite often experience in the international conferences. We are very useless in the mornings for a long day. Anyway, and this is on the way of return. So the LD cycle is the phase delayed by 8 hours at this day. And you can see kind of quick recovery. So here you can see many interesting stuff. One is this slow relaxation, slow adjustment to the new schedule in the case of eastbound trip, and quicker recovery in the case of westbound trip. There is a strong asymmetry. And there is a question why this is so slow, the adjustment is so slow. And there is actually the asymmetry of recovery process in a statistically well-defined manner. So this is the case of phase advancing jet lag. So there are many mice in this case, probably 10 samples, 10 subjects here. And please look at only black curve. This corresponds to the case of wild type mice. And you can see the onset time recovery slowly to the new time schedule. And it takes about 1 week or 10 days. And in the case of phase delaying jet lag, the recovery is pretty quick. And here I show the PS50. PS50 is time to achieve 50% recovery in activity onset or offset times. Okay, so basically from here to here. So it looks like about 5 or 6 days, right? So this is 5 days. And in the case of phase delaying jet lag, the recovery is about 3 days. Recovery time is about 3 days. So the eastbound trip is much harder, much slower. And what makes the recovery so slow? Here is a big clue. What is happening is actually desynchronization among SCN cells when LD cycle is advanced by 8 hours. Here I show black, please look at again the only black curves. And this is before the jet lag and this is after jet lag. And this is time series of clock gene expression in SCN. And before jet lag, we have clear, so the mice have clear oscillation. Then after jet lag, you can see the oscillation is so weak, about for 1 week, right? Very weak oscillation persists for 1 week. And if we look at closely the gene expressions in the SGN, we get this kind of slides. These figures show, so these figures shows a kind of snapshot of gene expressions within 24 hours. And before the jet lag, the black points appears around this time. So this means a synchronization occurs and there is clear synchronous oscillations peaked at this time. But after jet lag, you can see black points everywhere. And this means desynchrony occurs within this tissue. And after 9 days of jet lag, we can see, again, nice synchrony. So desynchrony occurs when they experience the jet lag of +8 hours. And we suspect that this could be a primary reason for heavy jet lag symptom. This desynchrony is a primary reason. And we have these questions and answers. Question 1, what is the asymmetric response between advancing, advancing and delaying phase shift? And I will come to this point. So this is the answer, because the jet lag separatrix is on the side of phase advancing jet lag. And question 2 is, why do clock cells desynchronize when energy cycle is advanced by 8 hours? And our answer will be desynchronization naturally occurs for phase shift around the jet lag separatrix. And how can we avoid jet lag? Okay. And to tackle these problems, we propose these phase oscillator models based on anatomy and various experiments. We have, so we describe the SGN as a phase oscillator groups, 3 groups inside the SGN. And actually, basically 2 groups are important, the group 1 and group 2. And this is the main body of the oscillators, and they are interacting with each other with this function to make the phase distribution between these oscillators. I put the parameter alpha here. And the influence of light comes via this oscillator Zell and expressed in this coupling function here. So the oscillator 1 try to synchronize to oscillator Zell in this function and try to synchronize with oscillator 2 in this function, but with some phase shift alpha. Okay, so this is our model. Okay, now let me answer to these questions. So what is the asymmetric response? And our answer is the jet lag separatrix. Actually, to explain this one, I do not need the help of mathematical models. I just briefly mention in this text. So there are 2 ways to adjust your clock to a new time zone. You can either speed up or slow down your clock, right? And then there must be a critical jet lag at which your clock changes the strategy, either speeding up or slowing down. And this critical jet is called jet lag separatrix. This is an important notion, and we named this one as a jet lag separatrix. And this is a case of mice, a certain mouse. So if we give a jet lag of +8 hours, you can see the clock speeds up. And if we give a jet lag of 12 hours, the clock slows down. So there is a separatrix between these times. And we suspect probably +10 hours, there is a separatrix in mice. And certainly recovery becomes slow for jet lag close to the separatrix because the effect of speeding up and slowing down almost balance. And this is the reason why +8 hours jet lag has a slow recovery compared to the -8 hours jet lag. Okay, so the question 2, why do clock cells synchronize when LD cycle is advanced by 8 hours? And our answer is pretty simple. Suppose that this is a phase of LD cycle, and this is a phase of clock cells. And remember that our clock is not a single, but a population of oscillators with distributed phases like this. So before jet lag, we have this kind of state, so that our phases are distributed. And if the LD cycle is suddenly shifted, this one, then some oscillators try to speed up and some oscillators try to slow down. And so as a transient process, we have desynchrony. So we believe that this is actually the case in what's happening in our brain. And the final question is, how can we avoid jet lag? So as I mentioned, so this is our mathematical model, and we tune the parameter values such that the jet lag separatrix locates at around 10 plus 10 hours. And this is numerical result. This is the amount of jet lag, and this is PS50 for each individual jet lag. And plus 0.3 is about plus 8 hours jet lag, and minus 0.3 is minus 8 hours jet lag. And our coupled systems, please look at this blue line. We have very slow recovery here compared to the single oscillator case. And this is because of desynchrony. And actually the desynchronized oscillation can be observed transiently for long in this model as well, mimicking the experimental result. So now we come to this idea. Recovery from jet lag should accelerate, and desynchrony of clock cells should be reduced if the approach of our clock system to the jet lag separatrix can be circumvented. And this is given by this way. So two-step jet lag. So I give 4-hour shift on the first day and then 4-hour shift on the second day. And this is a comparison. So this is a case of one-step jet lag. I am looking at the onset time as a function of days. And also this is a case of two-step jet lag. And you can see the recovery is faster in the case of two-step jet lag. And this is experimental verification using mice. And you can see this is a one-step jet lag, recovery is slow. And we use the same mice and give these two-step jet lags to the same mouse, and you can see the recovery is much quicker. And this is the statistical data and showing that the two-step jet lag is much faster, significantly faster than the case of one-step jet lag. Okay, I understand mice. So how about human? So this is basically final slides. I'm running out of time. Okay, so I got a wonderful subject recently, and I took this guy to Germany. And this is Japan, and this blue bird shows the sleep time of this guy, this baby. And here is Japan, and in Germany, he was a good boy, so he sleeps during night. But after we got back to Japan, we have kind of disaster here. He couldn't sleep for long, 8 hours or 6 hours during midnight. So we suspect desynchrony actually occurs in this guy. And we made another experiments. So we took this baby to US and we tried two-step jet lag. At first we went to Hawaii and then California. And we do not see any desynchrony in this sleep rhythm. He has minor problems here. He didn't sleep well, but basically it was okay. So our method works for this baby. And this is a kind of analysis of the sleep time rhythmicity. And for one-step jet lag, there is a big problems after backing from Germany. And this is a case of two-step jet lag, no problem occurs. Actually, these data are taken by my wife, thanks to my wife. Okay, so summary of issue 3. And this is a final summary. I'm sorry, I was so first on the last slides. Thank you very much.
Thank you very much for these exhaustive glimpses into the use of oscillator models. Now we have 10 minutes for questions. Please, are there questions online? Maybe I may start with one of my questions. Of course, most interesting is this jet lag phenomenon. And you showed the slide when you told that there is a special area in the brain. But is this area in both hemispheres of the brain or in a common place, or how does it work?
So
you
your
remember
question,
just yes, that one.
yes,
That the eye is connected to this area, but we have two eyes and two hemispheres, and the eyes are crossing even with the neurons.
Exactly. So the optic nerves connect to these regions. Okay. Okay. And in my model, actually, this region model that region. Okay. And the other regions are connected kind of indirectly. So that's the reason why I invented this model.
But the left and right hemisphere is also synchronized, so they also come together, right?
Yes, so they are synchronized well, so we didn't distinguish them.
I see. Any other questions to oscillators and synchronicity?
So if I may put a question. So first of all, thank you, Professor Kori, for this very pedagogical and wonderful talk. It was a pleasure listening for it. Of course, you are from the Kuramoto group, so I understand that you really like the phase-coupled oscillator models. But I'm just wondering whether with pulse-coupled oscillators, it could be explained both phenomena that you were discussing. So you were insisted only on this phase-coupled approach, but taking approaches where the coupling function is not continuous, just acting as a pulse-like phenomena, would it be possible? Because I would assume also that for fireflies, for instance, pulse coupling is more relevant than for phase coupling.
Okay, so thank you very much for this question. Actually, for example, so let me try as a first explain the fireflies. As you mentioned, yes, fireflies should be modeled with these pulse coupled oscillator models, right? So that was your question, I guess. And
that's right.
Yes, and what I want to say is if the coupling is weak compared to omega, so this model and Kuramoto type phase oscillator model are basically almost equivalent. Only if the coupling is larger than the compared to the frequency, this the pulse coupled oscillators behaves differently from the smooth Kuramoto type oscillator model. So if we find the special phenomena in a strong coupling regime, we should use pulse coupling. Sorry. Did I answer to your question?
Yes, I understand. So you want to say that through this P function, you can introduce the pulse coupling, or you can shift between the pulse coupling and phase coupling.
Yeah.
Okay, thank you very much.
Thank you.
Good.
And actually, in my jet lag study, I tried both types, and they are basically result in the same phenomena. Okay, thank you.
Fine. Any further questions to?
I have a general question. You tried to make this Kuramoto model fit real world data, but I'm used to Ising model where we don't do this. We look at a critical point and we find that it's universal. We fit critical exponents and things like that. So does that work as well for Kuramoto model? Is there a Kuramoto universality class and so on? Okay,
very good question, wonderful question. Maybe I should show the synchronization transition. Which slide is it? So this one. Okay, so this parabola-like transition is kind of universal in the case of Kuramoto model. Actually, not that robust. For example, you can introduce, for example, where is the Kuramoto model in my slide? Okay. For example, you can introduce the higher harmonics in the coupling, then the transition behavior changes. And also by adding some noise, you actually, again, the transition behavior can also change.
By transition behavior, you mean you change universality class, or you lose
the
universality?
The slope changes from the square root to the linear case, and so on.
Okay.
Okay, and there is a wonderful review by Strogatz in Physica D in 2000 probably. From Crawford to Kuramoto, and there the universality class is discussed. And
okay,
please look at that paper.
Thanks.
Thank you.
Still time for questions. Don't be shy.
I would have a question, but it might be not so technical, it might make no sense. So I would like to ask, in statistical physics, usually when we have phase transitions, there is at least one observable that is diverging. In this Kuramoto model, is there any observable that is diverging? And if it is diverging, how do we compare to the experiments? Do we have to use renormalization here as well, or not necessarily?
So what is diverging? So maybe I'm not very sure about it. I have never concentrated on that kind of, so perhaps fluctuation, but I'm not very sure about it.
What about the number of oscillators? Is that diverging?
Number of what?
Oscillators, the N, the big N. Number of your oscillators.
Yes, infinity.
Yeah, that's a divergence. The X is divergence.
Yeah.
And K is
but his question is about some dynamical property occurring at this transition point, right? So
okay, yeah. What derivative of R is then?
Yeah, derivative of R, yes, certainly, you're right. And if you look at the dynamics of individual oscillators, I'm not very sure this divergence of R correspond to what. Maybe I just forgot, but anyway, sorry, my answer is not sufficient.
Yeah. So formally, as you see, that R is proportional to the square root. It's just like by magnetization and temperature. Then the derivative of this, which would be a kind of susceptibility of this system, is 1 over square root, which diverges at the critical point, right?
Yeah, you're right. Susceptibility should diverge. Yes. Yes, okay. You're right.
Thank you very much.
Some further questions?
May I have a comment and a question?
Yeah, please. First, the comment.
Yeah, the comment related to this divergence may not be applicable here, but in dynamical systems, it happens in many cases that when you arrive to a bifurcation point, which is basically this phase transition point, your escape time or time to settle to the attractor diverges. So, for example, when you are coming from the region of desynchrony and you are decreasing your coupling at the critical point, you may have a divergence.
Yeah,
I'm not sure.
Yeah, you're right. The critical slowing down should occur. Yeah,
something like that. Okay, and a question. Most of the time we use phase oscillators for modeling different types of oscillating phenomena, but it may be also important to consider the amplitude of oscillations. Of course, these are used in many cases when you also take both the amplitude and the phase. But how can we decide actually which set of or which class of models we should use?
Yeah, very good question. Yeah, so his question is about which model should be used, whether the amplitude oscillations or the phase oscillations. And to describe, for example, the dynamics of these 4 metronomes, honestly, I think I should use oscillators with amplitude. Because in the transient process, you saw that 2 oscillators have, let me see it again.
Great.
Here, small amplitude oscillations, large amplitude oscillations here. And this amplitude effect is quite important in this transient process, I'm pretty sure. But the final state is very simple synchrony. So just to understand synchrony, phase oscillators quite often suffice. And to model the realistic situations, in many cases, I think you should consider the amplitude effect. But that model becomes quite complicated in general. So that's why I often choose phase oscillator models to model even complicated models such as the circadian clock system. And that helps a lot about the understanding of these complex phenomena. And I think I didn't answer to your questions. Maybe I just expressed my impressions, but anyway.
The answer is it depends on the problem, which coupling
Yes,
you use.
yes, you are right. You are right.
Okay. Maybe, well, we have one short last question, if anyone is one so. If not, I think we used successfully the time, and thank you very much for this enlightening review talk. And then I think we have a further talk here, because we already had the break before this talk. I should ask whether Csaba Szabó is present in this virtual universe.
Okay, thank you very much.
Thank you very much, Professor Kori.
Yes, I'm here. You hear me?
So you want to start your lecture about Transylvania?
Yes, there's no break as far as I understand. So,
well, the break can be after your talk as well, because we had a break just before Professor Kori's talk.
Okay, so I will begin my presentation as soon as I get to the PowerPoint.
Let me just say a few words about Csaba also. He's one of the rising stars in history and archaeology here in Transylvania, Romania. He's momentarily at the Sibiu Hermannstadt University, but he has strong connections with all, let's say, history groups and all groups who are working in archaeology in Romania. So I was very glad that he accepted that he makes an introductory talk about Transylvania for those of you who are interested something about the culture and history of Transylvania.
Very well. Please start your talk.
Thank you very much for your invitation, and good afternoon for everybody. As far as I understand, this talk is about a compensation for all those who never visited Transylvania, and in these extreme times you miss the excursion probably. But I hope after the pandemic you will visit Transylvania, and I can share and show you some of the cultural backgrounds and heritage of this region. My talk will have three aspects: one short about the geographical and geopolitical position of Transylvania. So where is Transylvania? What is Transylvania in geographical and geopolitical terms? And then I will go very fastly a history from the 5th century BC till now, presenting the major changes of Transylvania and how this region was defined by major European historical events. And by presenting this historical kaleidoscope, I will show also some of the most important and well-visited, well-known historical sites of the region. So Transylvania, as probably many of you already heard from
or know from history or from novels of Bram Stoker or other kind of sources. It is part of the Carpathian area. It's inside the Carpathian arch of the mountains. It is part of the greater hydrographic area of the Danubian catch. Most of the rivers from this area are floating into the Danube directly or indirectly. So it is part of the Danubian area of Europe and the Carpathian area in geological formation. So it is a well-protected area by the Carpathians, but it has also mountainous regions and also yes, they're like a mountainous area, but also the famous Transylvanian depression in the middle of this region. As an administrative unit, Transylvania is part of modern Romania, and it has two meanings. Most of the people who are using this notion today, even in Romania, sometimes it has a confusion as Transylvania is a bigger Transylvania. As a region, everything which covers the inside area of the Carpathians between Hungary in the west, Serbia in the southwest, and Ukraine in the north. So basically everything which englobes the inner Carpathian region. But historically, Transylvania is a much smaller area of modern Romania. It's basically the middle area of the country. Why we are still using this notion in a modern times? Why Transylvania became a brand nowadays? One of the reasons is its history and its historical heritage. Sucianu in the 1980s and his famous book on the 3 historical regions of Europe argued that the Western civilization in Europe, which means, of course, France, the UK, Italy, Germany, it has a very strong influence also in the so-called Middle Europe or Central European area. So this area of Europe is somehow a bridge between West and East, the Western Greco-Roman civilization and the Eastern cultures of ancient history, but also between Catholicism and later the Reformation and the Orthodox religious landscapes. So it has in all of the historical periods, Transylvania is part of this Mittel-Europa, Central European region. It's one of the last and most eastern parts of this second region of Europe. So this semi-peripheral area of Europe, as if we use the space hierarchy and the political hierarchy of Immanuel Wallenstein, Transylvania is somewhere between semi-periphery and periphery of Europe. If the core, the central of Europe is the Western culture, Western civilization, the Romantic art, the Gothic art, the Renaissance, everything is coming from the west to the east. Then Transylvania has all of these artistic reforms, but also the cultural influences, religious changes, and the social or industrial changes, the scientific changes arrives in Transylvania very early, with few decades or even a few years of break. So just few years after the Western civilization produces a new idea, an artistic or an abstract or a scientific or a social reform, you will find also in Transylvania after a few years of time lapse, but it definitely represents one of the semi-peripheries of Europe. There is also difference, of course, in quality and quantity when it comes to all the productions, the cultural and historical productions of Western Europe, and if you compare with Transylvania. But this you will see in the following. So if we begin with antiquity, Transylvania is again reproduce this semi-peripheric area of Europe. It was part of the Celtic world in the Iron Age. So 2,500 years ago, Transylvania is part of the Celtic world, but in a very marginal peripheric area of this civilization. As you know, the famous Druids and from the UK, England, the Gauls in France, the major Celtic oppida, the major Celtic settlements in mid-Austria and Bavaria. All these influences are present also in Transylvania, but in a very, very limited version, mostly objects which are traveling through merchants and commercial routes, which are in Transylvania. So in the 5th century, from the 5th century BC, Transylvania is part of the Celtic world. And later, the very interesting phenomena will happen between the 5th and the 1st century BC. Transylvania will be part of 3 major cultural influences. From the west, we have the already mentioned the Celtic influence, and from the south, we will have here slowly entering a new civilization, a new type of culture, the Dacians. The Dacians, which are a Thracian people from south, mostly from Montania area. They are entering slowly the Carpathians, passing the Carpathians, and will live in middle of Transylvania in the late 2nd century BC. So this area will be a confluence between this Balkanic culture, the Dacian civilization, and the Celtic culture. But as these maps shows, these black spots representing the Greek amphora and the Greek objects which are produced in the Hellenistic world. So the famous Greek world in East Europe and the Mediterranean Europe are arriving and are used already in the 5th and 1st century BC. And as you will see in the second map, these dots appears already inside Transylvania in the end of the 1st century BC. So the Hellenistic culture enters also Transylvania. It became a melting pot of cultures between West and East. The Hellenistic Greek-speaking world and the Celtic world are united in this area, which makes a very unique, a very interesting place in Europe in this period. They are using Greek objects, but in a very local versions of these objects. They are producing the pottery and they're producing the bronze vessels, but imitating the shapes and the forms of the Roman materials. So it's a very interesting transfer of the local materiality, the material heritage of the Hellenistic world, but in a very local semi-peripheric version. And this is, we will see that it basically will happen in every single moment of Transylvanian history. Dacians, as I mentioned, those people who will live in the middle of Transylvania. There are many tribes. Usually they are living separately, but in 2 or 3 moments in the history after the 1st century BC and until the 2nd century AD, so more than 200 years, there were moments when these tribes were united. The unification of these tribes, of course, was very short term, and it was not a state, as sometimes in history they claim, but it was an alliance, a political alliance between these tribes. But this moment when King Burebista, known from the Greek and Roman sources, united the Dacian tribes, they had already a direct contact, cultural relationship with 3 major cultures: the Celtic world, the Romans who are arriving from the south and southwest part of Europe, and they already mentioned the Pontic area, the Greek cities near the Black Sea and the coast of the Black Sea. So this Transylvania is now having a direct cultural, economic, and political clash or relationship with these 3 major areas of Europe. The Dacians also left many interesting sites. The most famous and most visited one is Számszegetusa Regia, it's their capital city in a beautiful natural environment, and it's a World UNESCO Heritage Site, so it's really worth to visit. The big change in the history of Transylvania and the history of this region generally is when Transylvanian territories will be part of the Roman Empire after 106 AD for less than 170 years. It's a very short period. It was not a good idea for the Roman Empire to maintain this territory for such a long time. It was, you will see that it was part of a peripheric area of the Roman Empire, one of the less populated and less urbanized area of the Roman Empire. But still, the heritage of the Romans are very important for Transylvania because they built two major, they left us two major heritages. One is the infrastructure and their cultural heritage. They built the cities they founded. They will represent the foundation. Most of the cities represent the foundation of the medieval infrastructure. The Roman roads are still used in medieval times and represents basically the major economic routes inside Transylvania. And of course, in the 18th century, Romanians will use the Dacian province, the Romanity, the Latinity of this culture in their nation-building project from the 18th century even till the 20th century and now. So Dacia has a cultural heritage and also an infrastructural heritage, which is still has an impact in modern Romania and Transylvania. If you visit every museum in Transylvania, you will find a lot of Roman monuments. Most of them are local products, but there are many very beautiful Roman materials coming from all over the empire, from Syria to Britannia, from North Africa to Pannonia. So there are many objects which were circulating in the Roman Empire, of course, together with the military, and there was also human and material mobility. So Transylvania in this period, and for the first time in its history, became part of an empire, a very dynamic world. There are many archaeological sites you can visit, for example, in Porolissum, and also in Olpia Traiana Sarmistegetusa. Of course, they are not like Pompeii or other famous Roman cities preserved perfectly, but they represent a very important heritage in the local tourism, and hopefully they in the future they will be transformed into a cultural value. In the 4th and 10th century, Transylvania became a very dynamic corridor of mobilities. All of those people who will pass this area in this more than 6th, 7th century period, the Gothic, the Japedic people, the Avaric people, the different Slavic groups, and finally the Byzantine influences. These people will never created a statehood. So Transylvania, after the Romans were left Transylvania, lost its statehood. So it was not part of an organic state, but it was lived, and it was a territory which gave home for many people, many cultures, different cultures, who stayed in this area for a few decades, usually a few decades, or the longest period in the 8th, 9th century, the Slavic people and the Byzantine influence we can observe for more than 200 years. The most important heritage of these, the great mobilities and the great, in this period of the 4th and 10th century, are the beautiful treasures. As you can see also here, treasures from Szilágysomlyó, Apahida, and many other famous treasures from this period represents not only the richness of these tribes and their leaders, but also a direct connection with Byzance, Constantinople, which was the new capital of the Eastern Roman Empire. All of these objects represent the influence from Byzance, from a very strong Eastern culture, Orientalism. The big change and the very important period is the 9th-11th century, which is also a problematic moment in Romanian and Hungarian historiography. There are still ongoing debates about this period, who was living in Transylvania in this period. There are many theories, of course. But the most important things is that in the 9th century, when Hungarians arrives in Transylvania, this region again is between two major cultural influences. One is the Frankish Empire from the west, and the other one is the Bulgarian Empire and the Byzantine influence from the east, and Southeast Europe. So these two influences, cultural and political statehoods, are between Transylvania. So they englobing this area. So Hungarians arrives in this area populated by Slavonic people, Bulgarians, and very probably also the Latin-speaking Romanians were already part of this big East European cultural mixture in this period. For the first time after the Roman Empire collapsed, Transylvania will be part again of a statehood. That is the Hungarian kingdom between 1009 and 1526. So for more than 500 years, Transylvania is part of the Hungarian kingdom. But as you can see also on this map, with a very interesting special statehood. So it was not independent. It was, of course, part politically and administratively was part of the Hungarian kingdom and administration, but with many autonomous regions. The Saxons, the German population in the south and the southeast, they had their autonomous territories, self-government, and also the Székely people, the settlers, who were protecting the margins, the edges of the Hungarian borders. So it was already in this Middle Ages, Transylvania had a very interesting statehood. And we will see that everything which was produced in the western part of Europe will arrive in the Hungarian kingdom and a few years later in Transylvania. One of the most fascinating heritage of Transylvania, and now it's one of the most visited sites, are the medieval heritage from this 500 years I mentioned when Transylvania was part of the Hungarian kingdom. Most of the sites you can visit are from this period. For example, the famous St. Michael Cathedral in Alba Iulia is from 1009 AD, so it's more than 1,000 years old cathedral. There are also several Romanic churches from the 12th century, for example, in Gioagiu and Ákos. These are also part of the Transylvanian heritage. Cisnedeara, again, from very early period of the medieval times. 1241 represents an important moment in Transylvanian history, the Mongol invasion. The Mongolian invasion, unfortunately, destroyed many of the cities and the infrastructure of Transylvania. So somehow it's one of the big tragedies of this region, the Mongol invasion, and all of these buildings you see are the few buildings which survived actually this invasion. After the Mongol invasion comes a new age of urbanization and the new type of art. This is the Gothic art, which arrives in Transylvania more than 100 years later than in Western Europe. The famous French and English or German Gothic cathedrals, of course, are earlier and much bigger, but we have our own version with many specific and local aspects. So Gothic art in Transylvania you see in almost every city. This is from Sibiu, for example, the big church cathedral of the Saxon community. Brasov, the so-called Black Church, which was burnt in the modern ages, and the Church of St. Michael in Cluj, again, represents one of the most exquisite and well-known examples of Transylvanian Gothic art. Another very important heritage of this period of the Hungarian kingdom in Transylvania is the Saxon heritage, the fortified churches of the Saxons. There are more than 200 of these. It's one of the biggest built heritages in Transylvania. Almost every village in the Saxon land are symbolized by their monumental fortified churches. What you can see here are only some of the well-preserved examples. Unfortunately, many of them are now in imminent collapse and danger because of the Saxon community unfortunately left the country in the 20th century. So it represents one of the big issues of Transylvanian cultural management and project and cultural heritage management, how to deal with this unbelievable and very rich medieval heritage. There are also many castles and fortifications from this period, from the Hungarian kingdom, especially after the Mongol invasion. Most of the fortresses were rebuilt in stone. Most of them are in natural environments near villages, but some of them are part of urban fortifications like in Cluj, Brașov, Sibiu. These cities have some of the best preserved city walls, medieval city walls, still visible today. One of the most visited medieval castles are from Vajdahunyad, Hunedoara, which was built by the Hunyadi family, who gave two of the most well-known personalities of Transylvania. Hunyadi János, Iván von Hunyadi, who was the hero of the famous Belgrade battle, which was saving Europe from the Ottoman Empire for more than 50 years. And if you hear every day at 12 o'clock the ringing of the bells in Europe, it marks the victory of Hunyadi János every single day. Still today, the bells are ringing at 12 o'clock in most part of Europe. And he was the owner of this castle. One of the most best preserved medieval towns, almost completely preserved city wall and medieval structures still visible are in Sighișoara, Segesvár, Szezburg, is also part of the UNESCO World Heritage. So it's really a wonderful town. It's a mini Prague. You can see all the essentials of Transylvania in one city. There are also monasteries which represent again the most eastern part of the Western culture of monasteries and monks. The famous Cistercian monastery in Kerc in South Transylvania is the most eastern monastery of this type in Europe. If you go in Székelyföld, in secular land, in the very edges of Transylvania, you will have also medieval heritage there. The famous churches represented, painted with 14th, 15th century paintings representing medieval scenes. And here you can see Saint László, Saint Ladislaus, the Hungarian Night King, for example. And the Romanian medieval heritage, one of the few examples and really a remarkable building is the Dansus Church from the 14th century, built in the Hatzeg area, which was a very early medieval region of the Romanian communities. So this is also a very important building representing the three major nations of Transylvania living in the medieval ages, the Hungarians, Székelys and Hungarians, Saxons and the Romanians were living in this area in the Hungarian kingdom. Things are changed in the 15th and the 16th century when Transylvania became so-called independent, quasi-independent. It was again on the edges of something new. The Ottoman Empire conquered most of southeastern Europe. Hungary was divided in three parts. The middle part of Hungary became the Ottoman Empire conquered the middle part of Hungary. A very interesting shape, as you can see here, a U shape became part so-called Hungarian kingdom, but actually it was under Habsburgic rule. The Austrian emperors were ruling in this area, and basically Transylvania was the only part which preserved the most interesting values and cultural heritage of the ex-Hungarian kingdom for more than 150 years. This region in the 16th, 17th century will have big changes which still visible in Transylvania. Protestantism, which arrives in Transylvania a few decades after the German Reformation. The 30 Years' War, where Transylvania became for the first time an important political factor and participant in political actions in Europe. And there are very important demographic changes in Transylvania in this period, which will mark also the future of Transylvania, because in this period, in the 16th, 17th century already, Transylvania, as you can see here, is the most diverse and ethnically most complex region of the Carpathian Basin, the Carpathian area. Romanians, you can see here in green, are representing around 40–50% of the population in that period. Hungarians and Germans the rest of the population. So Hungarians are in red and Germans in blue and yellow. So these three nations, which are very diverse religiously, there are many differences also in social differences between these three groups. And these differences and cultural clashes will define the Transylvanian history in the followings. What we have visibly from this independent Transylvanian period are palaces, especially of the aristocracy. There is the famous palace of the Princeps in Alba Iulia, and many aristocratic palaces from the Renaissance period, especially the big Transylvanian aristocracy, the Banfi, the Haller, the Bethlen families. They built most of these aristocratic residences, which are still visible. Some of them are in bad shape, others are restored recently. The next step, when Transylvania again became part of an empire, is in the end of the 17th century, beginning of the 18th century, when Transylvania is again part of an empire. So after the Roman Empire, many hundred years later, Transylvania is again part of an empire. This empire is the quintessence, what we name today as Mitteleuropa, or Central Europe, because Central Europeanism, Middle Europeanism was defined in this period by the Habsburgic Empire. As you can see here, Transylvania is again the edge of this empire, the very east part of this empire. So, but it represents a very important opportunity to this region, because it will be part of the same administrative, political, cultural unit, together with Prague, with Brno, with Zagreb, with Ljubljana, with Budapest, Vienna, and many other cities of this large empire. So Sibiu, Cluj will be in the same empire with Prague, with Ljubljana, for more than 200 years. What we have from this period as a heritage, as a visible built heritage, is the famous fortification, the star-shaped fortification of Alba Iulia, the big salt mine of Turda, for example, the big galleries of Turda, and many other industrial buildings. The heavy industrialization begins during the Habsburgic Austrian rule, and change definitely will change the urban landscape of Transylvania. We have many Baroque buildings, the famous Baroque architecture. There are many mini Viennas, if you want. So it's a copy of the high elite of the Habsburgic aristocracy. For example, Samuel von Bruckenthal will build this beautiful summer palace in Avrig, and the famous palace in Sibiu, which is the Museum of Fine Arts now in Sibiu, Hermannstadt, the biggest Saxon city. Or the Banfi Palace in Cluj. It's again one of the famous Baroque palaces of the 18th century Transylvania. But there is also a very important scientific boom in Transylvania. all the big ideas and the scientific revolution of the Illuminism in the 18th century will arrive in Transylvania very early. Actually, it's one of the first books, translations, manuals will arrive and will be produced in Transylvania. Here are some of the big, almost perfectly preserved libraries from this period. The Batyánium, you can see here from Alba Iulia, and the Telekiték or the Teleki library from from Târgu Mureș, Marosvásárhely. So these are the two best preserved libraries from the 18th century. But we have also in Sibiu the famous Brukenthal library, which again reflects very beautifully what the aristocracy and the elite was reading in this period. Transylvania produced also very many famous scientists in this in the early 19th century. As far as I know, there will be a presentation about the Bolyais, so you will know more about their lives. So their life and their mobility in the Habsburgic Empire was possible because of this new political environment where Transylvania is part of this Mitteleuropa, Central European region. But beside these good things and positive things, unfortunately, there were some negative things which arrived already in the 19th century. And that is mostly because of the nationalities and nationalisms will rise after the French Revolution. Of course, every single ethnic group, every single nation will have their own political aim and political narrative, which is usually clashing with the others. You can see here, Transylvania is one of the most diverse, ethnically most diverse areas of the big Habsburgic Empire. We have here Romanians, Hungarians, the Greens, and Germans. But because the Habsburgic Empire was extremely mobile and dynamic, in this period, in the end of the 18th, beginning of the 19th century, we have already Bulgarians, Serbs, and even Irish soldiers, for example, serving in the Transylvanian armies, and even a governor, for example, of Transylvania was an Irishman. So it's a very dynamic, a very mobile society, and this is one of the big issues of the 1848-1849 revolution, when Transylvania has, for the first time in its history, some ethnic clashes and conflicts. The solution of the Austrian emperor and the big politics, unfortunately, was not to resolve these ethnic problems, but to the solution was a coalition between Hungary, the Hungarian aristocracy, and the Austrian Empire. So between 1867 and 1918, they changed the Habsburgic Empire into a new confederation between Austria and Hungary. So Austro-Hungarian Empire, or Austro-Hungary, is the new political formation which existed for more than 50 years in this area of Europe. And this will represent the last period when Transylvania was part of an empire. What we have from this period, you can see here in this map, is the railway network of the Austro-Hungarian Empire. It is very visible that Transylvania is again the periphery of this Middle European culture. It takes 20 hours from some parts of Transylvania to reach Budapest or Vienna, the two capitals of this empire. So it was unfortunately much more isolated, also infrastructurally, but sometimes culturally too. Of course, there were some exceptions. For example, Cluj-Kolozsvár was one of the exceptions of these, because in the Austro-Hungarian period, many big urban cities will have massive urbanistic projects, and basically, if you will visit every Transylvanian city, half of the buildings are from the Austro-Hungarian period. So it's they change radically the urban landscape of Transylvania, and also the infrastructure And this heritage is still visible, is still with us. It's part of the Transylvanian cities. Here you can see, for example, the Art Nouveau secessionist buildings of Oradea, Nagyvárad. Big theaters were built, big palaces of justices in every Transylvanian city, like in Cluj, you can see in this photo. Or the most important institution in Cluj was the foundation of the university in 1872, which represents a big step in the life of this city. But basically, Cluj became the capital, the cultural and the scientific scientific capital of Transylvania. It was this university, the Franz Joseph University, was very important because of its mathematical school, medical school, but also a philological school. It was very famous not only in Central Europe, but it has already a European fame. Many scholars reached European fame. So this is the heritage of the Austro-Hungarian period. But of course, not only Hungarian heritage, we have many other architectural landscapes and beautiful buildings from the secessionist art or Romanian institutions. This period represents also for Romanian groups in Transylvania the moment of nation building and 40 years of legal fights with the Parliament of Budapest. Here you can see, for example, the Astra Association, the building of the Astra Association in Sibiu, which was one of the most important cultural institutions of the Romanians. And this represents also their founding institution for human rights, for political rights. They tried to negotiate with Budapest. Their aim as uniting with the rest of the Romanians south of the Carpathians, outside the Carpathian Arch, was realized only in 1918. And of course, due to the consequences of the First World War and the Trianon Treaty, when Transylvania became part of Romania after 1920. And this new situation created also a very interesting cultural mixture, because till now, as you can see, Transylvania was in every historical moment was the very eastern edge of Central Europe. It was from antiquity till 1918, Transylvania was always part of a Middle European, Central European mixture of cultural confluences. After uniting with the Romanian kingdom, Transylvania faced also a very interesting change when it becomes part of Southeastern European influences. So now we will have a very interesting mixture of Southeastern Europe and Central Europe in Transylvania. This is the map of Greater Romania in the interwar period between 1820 and 1940, sorry. And you can see also in this map that the most diverse, ethnically and culturally, the most diverse area of Greater Romania was Transylvania, the Banat area, and of course Dobroja, which has many ethnic groups and a very interesting cultural mixture, at least in the 1920s and 30s. So Transylvania was, after uniting with Romania, will have a significant Hungarian minority in Székelyföld especially, but also in the western borders. And in this period, in Transylvania, we still have a very important German and Jewish minority. Urban landscapes are changed in the 1920s. Many Romanian cathedrals are built in the cities, especially, which represent now a new cultural symbolism in the urban landscape. New centers were created to mark a new age, a new period in history of Transylvania. The biggest tragedy, I would say, after the Mongol invasion in the 13th century was the division of Transylvania. Unfortunately, in 1940, Hungary invaded or reconquered Transylvania with the help of Germany, Nazi Germany, and Italy. But unfortunately, only half of Transylvania was conquered, and the other half, the southern part, was remaining in Romania. And this division, unfortunately, is still visible today in ethnic, in cultural, and in many other senses. This period in 1940, 1945 is not marked only by this event, but especially by two major losses which Transylvania will suffer. One is the loss and the deportation and the mass destruction of the Jewish minority in the Holocaust, and after 1945, the German deportation, the Saxon minority is punished with deportation in 1945. And of course, during the 20th century, in the second half of the 20th century, will mark also almost the complete disappearance of the German communities in Transylvania. So after 1241, in the medieval ages, the Mongolian invasion, I would say that this is the biggest loss, the biggest tragedy of Transylvanian society, when it lost more than two of its important cultural and ethnic compositions. In the communist period, of course, the Ceausescu and the whole communist regime, more than 50 years, they tried to completely change the historical, demographic, and cultural landscapes of Transylvania. Massive urban destructions were happened. Of course, it was part of the industrialization. They changed not only the urban environments, like, for example, in Cluj, you can see here the medieval church of Kolozs Monostor, Cluj Monostor, but also in many other cities, like in they already saw the famous Hunedoara Castle. They built a huge factory near the castle, so it was happening in every single city, in every single settlement. But also in the 1980s, already in rural environment, there is a massive national project of the ruralization, the destruction of rural environments. Nowadays, fortunately, after 1990, things are much better. Transylvania, the historical part of Transylvania, represents the middle part of Romania. But as I saw in the first map, some people are still using the Transylvania as a notion also for the western part, western borders of Romania, which are also very diverse, ethnically very diverse area. Germans, Hungarians, Serbs are living together with Romanians in this area too. As you can see on this map from 2011, Transylvania is still the most diverse, ethnically the most diverse area of Romania. The other parts in the south, Oltenia, Muntenia, Moldova, is much more mono-ethnic, and the same pattern you can observe also in the religious diversity of the country. The most diverse, the most complex region is Transylvania, the Banat, and the Catholics in Moldova, which are actually also an influence or a heritage of the Hungarian medieval kingdom, the Chango people who once they were Hungarian speaking, now a big part of them are not speaking anymore, unfortunately, their Hungarian language, but they preserve their religion as Catholics, Roman Catholics. So you can see this ethnic diversity and religious diversity is clearly marked even today as a very interesting heritage of this history in Transylvania, which was always part between East and West. This cultural mixture and the environment now is used as a brand in Transylvania by Cluj, especially, which is now more than 500,000 people living in the city and its metropolitan area. Transylvania represents almost half of Romania with more than 100,000 square kilometers. 6.7 million people, and we still there is 1.1, 1.2 million Hungarians living in Transylvania. 36,000 Germans left, unfortunately, from the original 300,000 Saxons. Now only 10% of them are still with us. But it still represents, after many people, as a Switzerland of Central East Europe. So I hope you will have the chance to visit this area, and you can discover, you can observe by your own this very interesting and very diverse cultural mixture, what we call as Transylvania. Thank you very much.
Thank you very much for this review of a quarter of millennia, no, 2.5 millennia, actually. I don't know, we have some 12 minutes left until the next session. Shall we get some questions to this history of Transylvania? Has anyone some questions? Maybe just a very minor point, if I may, Csaba. Are you still here?
Yes.
Yes. You mentioned Avars, Goths, Gepids. You did not mention the Huns and Attila. Is there any trace of that period?
Well, the Huns had their center was in southeast Hungary. Today, the Szeged area. We have Hunnic archaeological material. Interestingly, in the Banat and in Oltenia. Transylvania was not really their favorite area. They preferred lowlands. So
I see.
Very few. There are some tombs which are identified as Hunnic, but their preferred areas were the lowlands in the Banat and Oltenia.
It's easier to ride the horses there.
Yes.
Does anyone else has some question to this long history? Since it does not seem to be the case, I suggest to make a small break and then rejoin at the next session at 17:00 local time. Is that right? So, and thank all the speakers and for the talks in this session again. Thank you very much.
Okay, on the behalf of organizers, I would like to thank Csaba for his wonderful talk about Transylvania, and also for Tamás Biró for chairing this session. I guess it was a very interesting session again.
My pleasure.